folks! The following video is going to delve more into radical halogenation. I'm going to talk about the thermodynamics of this reaction, the regioselectivity of this reaction, and stereoselectivity as well. The first part of the video is going to talk about thermodynamic considerations. Recall that delta G, the Gibbs free energy, is equal to delta H minus T delta S. Delta H is the enthalpy term, and the minus T delta S is the entropy term, multiplied by the temperature. The reaction we're going to be considering through this whole video are radical halogenation reactions. This will involve treatment of an alkane, such as methane, with a halogen, X2. This radical reaction will form a new carbon-halogen bond, and HX. Let's consider this radical halogenation reaction from a thermodynamic perspective, first thinking about entropy. The starting material is 2 molecules, and the product has 2 molecules present as well. Because the number of molecules does not change, you can expect that delta S is approximately 0, meaning that the whole minus T delta S term is approximately 0 and is negligible. Delta G is approximately delta H, the change in enthalpy of the reaction. And we can estimate the change in enthalpy for a reaction using bond dissociation energies. Delta H for a reaction is equal to the sum of the bond dissociation energies for the bonds broken minus the sum of the bond dissociation energies for the bonds formed. So we're going to think specifically about the strengths of the bonds broken and formed for the halogenation of methane, where X could be fluorine, chlorine, bromine, or iodine. Here is a table with all of the relevant bond dissociation energies we need to compare these different values, and the delta H of reaction values when X is fluorine, chlorine, bromine, or iodine. The bond dissociation energy for the CH bond of methane is always 435, but notice that the strength of the XX bond changes depending which halogen X is. The strength of the carbon-halogen bond that's formed is different depending on the halogen X as well, and the strength of the HX bond also depends on which halogen you have. So to make thermodynamic considerations, let's calculate delta H of reaction for each of these different halogens. When X is fluorine, you take the sum of the bond dissociation energies of the bonds broken. This is the CH bond of methane and the fluorine-fluorine bond of F2. And from this, you subtract the sum of the bond dissociation energies for the bonds formed. This is the carbon-fluorine bond of fluoromethane and the HF bond. Overall, delta H of reaction is negative 432 kilojoules per mole. This is a huge negative number, meaning that this reaction involving fluorine is highly exothermic. This is a problem in a lab because it releases so much heat that the reaction is explosive. Because of this, we're not going to consider fluorination reactions for the remainder of the video. For radical chlorination of methane, where X2 is Cl2, delta H of reaction is a more reasonable negative 104 kilojoules per mole. So this is exothermic, but not extremely so, and because delta G is approximately delta H, we would expect that this reaction would be exergonic and spontaneous. Methane bromination using Br2 has a delta H of reaction of negative 33 kilojoules per mole, so less exothermic, but we would still expect this reaction to be spontaneous. And radical iodination, where X2 is I2, has a delta H of reaction of positive 55 kilojoules per mole. The fact that delta H is positive means that this reaction is endothermic, And because delta G is approximately delta H, that means that delta G, the Gibbs free energy, is endergonic. Endergonic reactions are not spontaneous. So although we can draw out this reaction involving I2 on the page, it won't work in the lab. So because of the problems with F2 and I2, for the remainder of the video I'm going to be focusing on radical chlorinations and brominations. Before explaining the theory of the selectivity of these reactions, I want to show you the experimental observations. We've previously seen that methane can be monochlorinated if methane is treated with Cl2 in the presence of light. From there, organic chemists also wanted to look at other alkanes with more carbons. What's experimentally observed is that if you treat this particular alkane, in which you have a tertiary carbon with 3 methyl groups attached to it, radical chlorination gives 2 different products, where you broke the CH bond of the tertiary carbon to give this product, and you also form the product where you break one of the CH bonds of a methyl group and add a new chlorine at that position. I'm not drawing it out here, but in this reaction as well, HCl is a byproduct. So because multiple products are formed here, I would say that radical chlorination is not regioselective, meaning you don't selectively add the chlorine to a particular position based on its substitution. If you treat the same alkane with Br2 and light instead, you form just one product. Because this reaction selectively forms one regioisomer of product, we would call this reaction regioselective. And what's observed is that the weakest CH bond, the tertiary one in this molecule, was broken, and the bromine selectively added to that position. So this is an interesting result, switching just from Cl2 to Br2. And we're going to have to think more about the rate determining step and thermodynamics in order to explain this result. Let's first consider the thermodynamics of radical chlorination. I'm going to switch up our alkane a little bit. We're going to be looking at ethane reacting with Cl2 in the presence of light to form chloroethane and HCl. The steps we need to consider the thermodynamics of are the propagation steps. The first propagation step is a hydrogen abstraction by the chlorine radical. This forms a carbon radical and HCl. And this is the rate determining step, so pay particular attention to this step. The CH bond strength of ethane is 410 kilojoules per mole, and the HCl bond dissociation energy is 431 kilojoules per mole. Calculating delta H for this reaction step, you take 410, the bonds broken, minus 431, the bond formed, and you get negative 21 kilojoules per mole. So in the case of radical chlorination, the hydrogen abstraction step is exothermic. Now let's consider the second propagation step, halogen abstraction. In this step, the carbon radical reacts with Cl2 to generate chloromethane and regenerate the chlorine radical. Recall that your propagation steps should sum to the overall reaction, and you should regenerate the propagating radical in the second step. Here are the bond dissociation energies for the chlorine-chlorine bond and the carbon-chlorine bond that's formed. Calculating delta H for this reaction step, I take the chlorine-chlorine bond strength, the bond broken, minus the carbon-chlorine bond strength, the bond formed, and I get negative 96 kilojoules per mole. So this step as well is exothermic. Here I've put these two propagation steps on a reaction coordinate diagram. The first step, the hydrogen abstraction, is exothermic by 21 kilojoules per mole, and this has the highest barrier of the whole reaction, meaning it's the rate-determining step. The second propagation step, the halogen abstraction, is also exothermic, and it has a smaller barrier because it is not the rate-determining step. The important takeaway from radical chlorination that I want you to remember when I discuss radical bromination is that the hydrogen abstraction step by the chlorine radical is exothermic. Now let's consider the bromination of ethane. This would be treatment of ethane with Br2 in the presence of light to make bromoethane and HBr. And here as well, we're going to look at delta H for the propagation steps. The first propagation step is hydrogen abstraction. In the case of radical bromination, it is a radical bromine that is present. This abstracts the hydrogen from the CH bond of ethane to make a carbon radical and HBr. The bond being broken in this case is the CH bond of ethane, and the bond formed is HBr. We could calculate delta H for this hydrogen abstraction step as being positive 42 kilojoules per mole. So notice that our rate-determining step, the hydrogen abstraction step, is endothermic in the case of radical bromination. Now let's consider the other propagation step, the halogen abstraction. This involves the carbon radical reacting with an equivalent of Br2. In this step, the bromine-bromine bond breaks, a carbon-bromine bond forms, and the bromine radical is regenerated. Here I'm showing the bond dissociation energies for the bromine-bromine bond broken and the carbon-bromine bond formed. Using these values, we can calculate delta H for this halogen abstraction step for the bromination reaction as being negative 92 kilojoules per mole. So this step, this halogen abstraction step for bromination, is exothermic. We can consider a reaction coordinate diagram for the radical bromination of ethane. The first propagation step, the hydrogen abstraction step, is endothermic. So I'm putting the energy of the carbon radical and HBr as higher than that of the ethane and bromine radical starting material. And this is the rate-determining step. So I've made this the highest barrier on the diagram. The second step, the halogen abstraction step, is exothermic. And because this is more exothermic than the first step was endothermic, the reaction overall, going from starting material to products, is exothermic overall, like we saw earlier for methane. The most important takeaway from this analysis of radical bromination is that the hydrogen abstraction step, our rate-determining step, using the bromine radical, is endothermic. So a different outcome than we had for chlorination using the chlorine radical. So let's consider the hydrogen abstraction step using a chlorine radical or a bromine radical, and let's consider these side by side. And one thing I want to remind you about is the Hammond postulate. This states that the transition state resembles the species that it's closest in energy to. And this species could be the starting material, an intermediate, or the products. So looking just at the hydrogen abstraction step, using a chlorine radical, this step is exothermic. Looking at the hydrogen abstraction step using the bromine radical, this step is endothermic instead. So notice in the case of radical chlorination, the transition state is closest in energy to the starting material. What this means is that in the hydrogen abstraction step, the transition state looks more like the starting material than it does the product. This means that the CH bond is barely starting to break, and the HCl bond is just barely starting to form. This means that if we look at where the partial radical character is, this is similar to like partial positive or negative charge, but for a radical instead. Because you had a chlorine radical starting out, the chlorine of this transition state has the big partial radical character present, meaning this mostly looks like a chlorine radical, and there's just a little tiny bit of partial radical character developing on the carbon that's losing its bond to hydrogen. Overall, I'd say that by the Hammond postulate, because the hydrogen abstraction step by the chlorine radical is exothermic, the transition state resembles the reactants. Notice in the case of radical bromination that the transition state is closer in energy to the intermediate instead of the starting material. This means that if we looked at the transition state, it looks more like the intermediate with a carbon radical and HBr. So in terms of the transition state, that means that the CH bond is mostly broken and the HBr bond is mostly formed at the transition state. So very different than the chlorination case. Because the transition state is closest in energy to the carbon radical, the carbon has a lot of partial radical character at the transition state, and just a little bit of partial radical character on bromine. Overall, this means that for radical bromination, the hydrogen abstraction step has a transition state that resembles the intermediate instead of the starting material, meaning the transition state looks like a carbon radical and not a bromine radical. So our different transition states have different amounts to which you have a carbon radical compared to a chlorine radical. So in the chlorination reaction, the CH bond is just barely starting to break, and in the endothermic radical bromination hydrogen abstraction, the CH bond is almost completely broken at the transition state. Now let's consider the hydrogen abstraction step by a chlorine radical, where you could potentially form a primary carbon radical, a secondary carbon radical, or a tertiary carbon radical. Notice that I've ranked these different carbon radicals in order of their stability, where the tertiary, more substituted one is the most stable. If we looked at the barriers going from the starting alkane and the chlorine radical to these different products, because the transition state is close in energy to the alkane starting material, the CH bond is only starting to break at the transition state, and there isn't significant carbon radical character present. This means that the substitution of the carbon radical that's forming isn't influencing the transition state very much. Now let's consider the hydrogen abstraction step for an alkane with a bromine radical. In this case, all of the carbon radicals are higher in energy than the alkane and bromine radical starting material, but still I've ranked them in order of their energies, with the most stable tertiary radical lowest. Here we would look at the transition states leading to these carbon radicals, and there is a big difference in energy of the transition states leading to those different carbon radicals. The transition state leading to the tertiary carbon radical is the most stable by far, because it puts a large amount of partial radical character on a more substituted carbon at the transition state. Overall, what you see is that in the case of radical chlorination, you get similar barriers leading to the different carbon radicals, and the similar barriers mean that the reaction is not regioselective. There's not much of a preference for forming a tertiary carbon radical compared to a secondary or primary one. We have a very different scenario in the case of radical bromination, where we have really different barriers that reflect the stability of the carbon radical present at the transition state, and this leads the reaction to be regioselective. You preferentially go by the lowest energy barrier possible to form the most stable carbon radical intermediate possible. So now let's return to our earlier experimental observations for radical chlorination compared to bromination. In the case of radical chlorination, the reaction was not regioselective. We can explain that this is not regioselective because there's not much of a preference for forming a tertiary carbon radical compared to a primary one. This is because that hydrogen abstraction step is exothermic and not regioselective. Instead, radical bromination is regioselective, and the bromine is selectively added to the most substituted position with a CH bond present. This reaction is regioselective because you selectively form the tertiary carbon radical. This is because the rate-determining step, the hydrogen abstraction step in the case of bromination, is endothermic. And the fact that this step is endothermic means that there is a preference for forming a more stable radical intermediate. These considerations are important when you're going to predict the products for a radical chlorination or bromination. And what you should do in the case of bromination is look for the location of the most stable radical that could form upon hydrogen abstraction. So for example, let's consider the following starting material being treated with Br2 in the presence of light. Because this is a radical bromination, you would look for a position with a CH bond present that would form the most stable radical intermediate. In this molecule, this tertiary position with a CH bond present would form the most stable radical intermediate. You could predict the product of this reaction by drawing a new carbon-bromine bond at this position in the product. Now let's consider the stereochemistry for radical halogenations. So far I've only shown examples where halogenation did not form a new chiral center, but it is possible that halogenation could form a new chiral center. This occurs in the following example. So I'm treating butane with Br2 in the presence of light. Because radical bromination is regioselective, I need to identify the position that the bromine would add to. This position that would form the most stable radical after hydrogen abstraction is a secondary position. It doesn't matter which of the secondary positions you choose, they would actually give the same product. And I would initially draw my product with a new carbon-bromine bond at this secondary position. Notice that the starting material was achiral, but the product has a new chiral center. Halogenation, if it forms a new chiral center, will generate both stereoisomers of product. In this case, you would draw products both with a wedge bromine and a dash bromine, and these are enantiomers, meaning this is a racemic mixture of product. The reason you get both stereoisomers of product has to do with the fact that the radical intermediate is planar. Once you form this planar intermediate, the halogen abstraction step can happen on either face of the planar radical. So, after hydrogen abstraction, butane forms the following radical intermediate. Notice I have 1, 2, 3, 4 carbons present. The carbon has 3 bonds, 1 to a hydrogen, 1 to a methyl, and 1 to an ethyl group. And the radical is present in a p orbital with lobes above and below the plane of the radical. It's possible that the halogen abstraction could occur with a bromine molecule coming in from above the plane of the radical. This would generate a new carbon-bromine bond facing up the plane of the page, and this is one enantiomer of product. But because the radical is planar, and the p orbital has lobes both above and below the plane of the radical, the halogen abstraction step could occur from below the radical instead, and this would lead to a new carbon-bromine bond pointing down the plane of the page, and this is a different enantiomer of product. Halogenation can occur at chiral centers as well. So let's consider the following alkane chiral starting material. And this is undergoing radical bromination. I want to identify the most stable radical intermediate that could form upon hydrogen abstraction, and that would be this tertiary position. It's observed that the new carbon-bromine bond of the product is present at this tertiary position, but even though I started with just one enantiomer of starting material, you get a racemic mixture of product. The reason you do not maintain one stereoisomer of product is because you lose the stereochemical configuration of the starting material when you form a planar carbon radical intermediate. So let's think about the hydrogen abstraction step. You start out with a chiral center, and you use the bromine radical to abstract the hydrogen from this tertiary CH bond position. This carbon position had 4 different substituents and was chiral in this starting material, but upon hydrogen abstraction, you form a planar radical intermediate. Now that the radical is planar, the halogen could add from either above or below to give 2 different chiral products. Okay, so to summarize some key information from today's video, what we observed experimentally and explained due to thermodynamic analysis was that radical bromination is slower than radical chlorination, but it is more selective. So in the case of an alkane starting material where you had both primary and tertiary CH bonds present, radical chlorination gave a mixture of products, whereas treatment of the same alkane with bromine in the presence of light selectively gave the product where the bromine was added to the tertiary position, which means that a tertiary radical selectively formed in the bromination reaction. And what we observe in terms of stereochemistry is due to the fact that the radical carbon is planar, radical halogenation is not stereoselective. So let's consider a bromination reaction of the following alkane. For brominations, you want to identify the most substituted radical intermediate that could form upon hydrogen abstraction. You would want to look at all of the different positions with hydrogens present on them and identify the most substituted of these. In this molecule, this tertiary position with a dash hydrogen is the most substituted position, and the carbon radical will form here after hydrogen abstraction. Because that carbon radical is planar, the bromine can add to it from above or below, and you would get 2 different stereochemistries of product at that position. Notice I had a second chiral center on the left side of the molecule, and that stereochemistry is unchanged in this reaction. It is only the chiral center that forms where the radical was present that I can have different stereochemistries at. Alright, that's it for this video. I will see you in class.